Hi everyone, this is going to be a quick video where we discuss how to design a controller using Matlab and with Locus. Let's have a recap of what we have seen before. Um, you remember from our previous discussions that if I have a plant G of S, this plant will receive some form of input and then will generate an output Y of S. Typically what we do is we close the loop by comparing this Y of S with some input R of S, which is my reference. The difference between the two will generate an error signal, and then the error signal is what I feed into a controller C of S, which will generate the actuating signal to drive the plant. We've talked about the different types of controllers. We saw that the most common one for linear systems is a PID controller that consists of a proportional term, an integral term, and a derivative term. Now you can have a combination of these three as well. You can have just a simple proportional gain or a PI, which consists of a proportional integral, or PD that consists of a proportional and a derivative term. Today we're going to talk about the PD controller. So PD controller is going to have a proportional term, let's show it with K of P, plus a derivative term, which is like KD times S. I can rewrite this in the form of KD divided by KP times, I'm sorry, let me go back here. So I can take a KD out, and then I can write KP divided by KD plus S. So that's how I can rewrite my PD controller. If you look at it this way, you will see that essentially the controller consists of a zero, which in this case is going to be at minus Kp over Kd, times some sort of a gain, which in this case is going to be my Kd. So if I want to design a PD controller, essentially what I have to do is I would have to add a zero to the system and then play with the gain in order to get to the behavior that I want. The best way to understand how this works is to work through an example. So let's say I have a system with an open loop gain of 1 divided by s plus 10 times s squared plus 3s plus 2. That's a third order system with no zeros. The desired behavior that I want for this system is to have an overshoot, which is less than 10%, and a settling time, which is going to be less than or equal to 2.3 seconds. So essentially, I want to know how I should find the parameters of my controller so that I can get to these two characteristics. Now, we have done this before for a second order system, and you know that it's a relatively easy approach where you would actually add the CS to your system and then find the closed loop poles and as a function of your KP and KD, and then find those parameters in such a way that you would achieve this overshoot as well as the settling time. Here, however, the system is third order. For a third order system, we don't have a closed form equation for the settling time or for the overshoot. So we're not going to be able to solve this by hand, which is why we have to do this using Matlab. If I want overshoot to be less than 10%, that indicates that my zeta has to be greater than or equal to 0.59. This is, of course, a calculation that you can do yourself. And then if my settling time is less than 2.3 seconds, that means 4.6 divided by zeta omega n would have to be less than 2.3, meaning that zeta omega n is going to be greater than or equal to 2. Now let's go to Matlab and see how it would actually design a controller now that we know we have these requirements for the behavior. So in Matlab, and this is something you can follow for the rest of the examples and homework problems that we're going to have in this semester. Essentially, first you would have to define your S as a variable of Laplace. There are different ways to do this. The way that I usually do it is I define S as a transfer function itself. Once I do that, then Matlab understands S as a Laplace variable and not just as a random variable that needs to have a number assigned to it. So now I would say my G, which is the system, is 1 divided by S plus 10 times S squared plus 3 times S plus 2. So that's my feed-forward transfer function, which, as you can see, is a third-order system. Now, in order to design our controller, we're going to be using a tool that Matlab has called SISO tool. SISO stands for Single Input, Single Output. This is a design tool for systems that have one input and one output, which is what we're concerned with in this course. In order to open that toolbox, the only thing we would need to do is to just type SISO tool, press enter, and it usually takes a little bit of time for the system to load the toolbox, and then once it opens up, I'll show you the different bits and pieces that it has. Essentially, we're going to be using SISO tool for a lot of design problems that we had in this semester. It allows us to plot root locus. It gives you a step response, and it does actually quite a lot of design tools for frequency domain, things that we're going to be talking about later on. So this is loading. What I will do is I will expand this window so you can see this better, and then move my video a little bit here. So as you can see, it has different options. You can have Bode plot for magnitude and phase. This is again something that we're going to be talking about later on. What we're concerned with right now is the root locus, and of course we want to see the step response. Now, right now, as you can see, this is blank because we don't have a system associated with the SISO tool. The first thing you have to do is you have to import your system into SISO tool so that it understands the dynamics. So what you do is you click on Edit Architecture, you click on this button, and the menu is going to open up. It has different types of configurations. The first one is really the one that we use. Notice it has our controller, it has G, which is my open loop transfer function, and it has a function for H. So what you have to do is you have to import some function for these individuals. Right now, the only thing we have is G because we don't know what our controller is. We are in the process of designing it, and we're assuming that H is a unity feedback. So what I do for G, I click on this import button, and this menu opens up that it allows me to either import data for that open loop transfer function from a mat file or from the workspace. Now, since I have already typed my G of S in the workspace, this is already here, and it shows G as a transfer function of order 3. So I just click on it to highlight it, and then I hit import. Once I import it, I hit OK. And now this function is going to be imported into SISO tool, and you can see that this is the root locus of my system that has 3 poles, one at -10, one at -2, one at -3. I'm sorry, one at -1 and -2, and the third one at -10. And then this is your step response. Now, we have some design criteria. We want to make sure that the overshoot is less than 10%. And let me make sure I remember correctly, and settling time to be less than 2.3 seconds. So what we can do is we can actually visually incorporate those design criteria here. So you would come to the page for root locus, you right click, and you would say, I want to add a design requirement. So design requirements, new. And a window should open up, and I would say my percent overshoot, I want it to be less than 10. When you hit OK, you see this region. So this white region, or the shaded region, is the region that has an overshoot of greater than 10%. This region, on the other hand, is the region in which the overshoot is going to be less than 10%. So this is the desired region for us. The other design criteria is for the settling time to be less than 2.3 seconds. Now, this is a little bit tricky because our definition of settling time, if you recall, is 4.6 divided by zeta omega. And this is the time it takes for the system's output to settle within plus minus 1% of the final value. Matlab's default definition for settling time is actually the time it takes for the output to settle within plus minus 2%. So when you have 2%, Matlab's definition would be basically 3.9 divided by zeta omega, and it certainly takes less time to settle within plus minus 2% than it takes to settle within plus minus 1%. So in this particular case, since I want my settling time to be 2.3 based on a plus minus 1% envelope, I'm going to have to update this to be related to what MATLAB sees as settling time, which is plus minus 2%. So this is quite easy. What I do is I would multiply my 2.3 by 3.9, which is the numerator for MATLAB's equation, and then divide it by 4.6, which is the numerator of settling time equation that we use. This is going to be 1.95. So in order for the system to settle within plus minus 1% of the final value in less than 2.3 seconds, it will have to settle to within plus minus 2% of the final value in less than 1.95 seconds. So I come back here to my CISO tool, and I add yet another design requirement, which is going to be a settling time of less than 1.95. Now, this area here is going to be my desired region. The one thing you see is that my dominant poles, that are these two guys, because this one is far away, the dominant poles are actually outside my desired region. So I'm going to have some sort of a controller that helps me push these dominant poles into the desired region. Since we're doing a PD controller, remember that it consists of a 0 as well as a gain. Let me come back here. My PD controller is essentially a 0 and a gain. So what I can do is I can first add my 0 to make sure that the branches of my root locus would come into this desired region, and then I can play with the gain. So in order to add a 0, what you do is you right click here and you would say add polar 0. You want to add a real 0. And wherever you place your mouse cursor, basically that's where your 0 is going to be. So let's put it at minus 15. When I place this in minus 15, you notice that the shape of my root locus changes. And of course, what you can do is you can start moving it around. And if you grab it and move it around, you will see that this whole graph will start changing. I can move it a little bit, to random directions until I can see that my dominant poles start coming into the shape, into the desired region. Notice that once I'm here, my dominant poles are essentially outside my desired region. That means with this particular 0, there is no way for me to get the design requirements that I want. So probably the best way to do is to start moving in the other direction. And notice as I start moving in the other direction, these branches of my root locus, these guys here, will start moving into the desired region. What I would like to see is the branches coming into this wide region. So this is basically a trial and error process, and you're going to have to move this around a little bit. You have to be careful to find the best spot. So if I bring it here, you can see that, yes, I'm basically, my root locus now is touching this intersection of these two lines, which means if I can bring my system or choose a gain in such a way that the poles come into that particular intersection, then I'm going to be within my desired region. Now, right now, the poles of my system, despite the fact that I have added the 0, my poles are at -10 and a -1 and a -2. Now, I can grab this purple dot that you can see, and by moving this purple dot, essentially what I'm doing is I'm increasing the gain of the system. This is exactly what we did in class when I showed you how in a root locus, every branch moves from one pole of the open loop system to a 0 of the open loop system or to infinity. So this branch of the root locus is moving from pole of open loop to 0 of open loop, and these two branches move from poles of open loop to essentially to infinity, because I have, remember, I have 3 poles and just 1 0. So one pole goes to 1 0 and 2 poles will go to infinity. And now what you can do in order to change the gain is you can grab this guy and start moving it. Once I'm moving it, this essentially means that I'm increasing the gain. And notice as I am increasing the gain, let me go back a little bit and do this a little bit more slowly so you can see this better. Once I am all the way here, my poles are, go all the way back. Yes, my poles are at -10, -2, -1. Now I am starting to increase the gain, and notice these two poles start moving along these two branches. What I want to do is I want to come close to this intersection, if I can get it exactly there. That is good enough. So here now, my dominant poles are essentially in the border or boundary of this desired region, which is okay. And this one is going to be a pole which is farther away from these two poles. It's not 10 times larger than them, so I cannot really ignore that, but it's not going to have a significant dynamic. So now this is a controller that I chose. I placed a 0 to take essentially take care of the 0 that PD has, and then I played with the gain in order to get the result that I want. Now this is my step response, and what you can do is you can right click to see the characteristics, and settling time here is going to be around maybe 1.7, and we wanted 1.95, so this is actually pretty good. Now what we can do also is to look at the peak response, which is going to be maybe around 0.95 versus a 0.8. So that's going to be less than 10%. Now, obviously, what I did was a kind of a graphic approach. And what I would like to see is what controller I ended up having. So what you can do is you come to the left side of your page. If you click on C, you can see your controller. So that's 15.59 times S5 plus 5.6. Let's come back here. So what I have is 15.59 times S plus 5.6. So that 15.59 is my KD, and 5.6 is going to be my KP divided by my KD. So that's how we design controllers using root locus and using CISO tool. I encourage you to repeat these steps that I did just to make sure that everything makes sense and you can do this approach. Later on, we will see that in future lectures, we will see actually how to do this for just a proportional controller or a PI controller as well. Okay, so at this point, I'm going to stop the presentation, and hopefully this makes sense. Go through the lecture notes, and if you had any questions, email me or I'll try to get back to you as soon as possible. Okay, thank you.